Bismillahirrahmanirrahim. Lecture number 17, Radioactivity and Half-Life. So in previous lecture, we did discuss something about the nuclear fission and nuclear fusion. And we did discuss something about the physics behind that, why we have got fission process or fusion process. So the main idea was like the iron atom is the most stable nuclei. So the element which has got the atomic number less than iron will try to fuse together to become more nuclear stabile. Uh, and the element which has got more atomic number than the iron atom will try to split their nuclei to become more stable. So that actually define another process, and that we call it as radioactivity. So radioactive decay or radioactivity or nuclear decay is a process in which the nucleus of unstable atom loses energy by emitting particle of ionizing radiation. The material that spontaneously emit this kind of a radiation are known as radioactive material. Normally, the radioactive process is random process at the level of single atom. That means like we cannot predict when the atom will have a decay. But yes, we can actually have a chance like we can actually have a large number of atom if we take it. Then we can actually measure or compute the decay process, and that come up as like the half-life of an element. So at the atomic level, we cannot actually properly predict when it will be, but at a mass level, we can just say like when the total element will try to decay, and that's what we actually measure in a half-life. So there are many different type of a nuclear decay or radioactive decay. The decay or loss of energy result when an atom of one type of nucleus, called as the parent isotopes or parent radioisotopes, transform to an atom with a nucleus of different state or a different nucleus containing different number of proton or neutron. That called as the daughter isotope or daughter nuclear radioisotope. In some decay, a parent and daughter are different chemical element, and that's what we call it as a nuclear transmutation. When we actually a nucleus is transformed into another type of a element. Uh, the first decay process that was discovered was the alpha decay, beta decay, and gamma decay. So what is an alpha decay? Alpha decay occur when the nucleus eject an alpha particle, and that is what we normally call it as a helium nucleus. This is the most common process of emitting nuclear, but a rare type of decay, in which actually we have got the two proton and two neutron are ejected from an element. So that come up as when we are ejecting two neutron and two proton, that's what we say like we have got a helium nucleus. So we have got a two neutron and sorry, no, two proton, and obviously combining with two neutron, that will come up as helium 4 nuclei. Um, in this kind of a decay, or what we call it as a cluster decay, because it is actually not a single nucleus, or sorry, single proton or neutron is released. So we have got a cluster type of a decay. In this kind of a nucleus, the atomic number is decreased by 2, or if I would say like the parent atomic number is decreased by 2, and the parent atomic mass is decreased by 4. So as I've said earlier, that the number of proton would actually tell you about the atomic number, and the number of proton plus neutron will be telling you about the atomic mass. So the mass number is reduced by 4, while the atomic number is reduced by 2. So we have got at the end of alpha particle, we have got a helium nucleus, and that is actually He42. Uh, where X obviously is called as a parent nuclei and Y is called as a daughter nuclei. For example, uranium 238, will actually decay into thorium 234 atomic mass, while thorium has got the atomic number of 90, uranium have got atomic number of 92. And that were by decaying process, we will be having an alpha particle of helium. Radium 88 would convert to radon 86 by emitting a helium nucleus. Um, as said earlier, like this kind of a decay or this kind of a process is known as the element transmutation process, in which one element is transformed into another element. The general rule should be like the sum of the mass number at both sides of the equation should be equal, and sum of the atomic number at both sides of the equation would be equal, should be equal as well. But later on, like in different experiments, it was noted that the mass of the parent was much greater than the combined mass of the daughter plus the alpha particle. Now, where this excess mass goes, actually, this excess mass is converted to energy in the other form and appear in a form of kinetic energy in a daughter nucleus and alpha particle. So that means like some of the energy would be required so the radioactive decay would occur. Now, the question would be if it is converted to the kinetic energy, so where the energy is going or which particle is taking the kinetic energy. So normally the thumb rule should be, or the thumb rule is, the particle which is actually having atomic mass less or less atomic mass actually would take the most kinetic energy. So in this case, alpha decay would take the most kinetic energy. Most of the kinetic energy is carried away by the alpha particle because it has got less massive than the daughter nucleus. Alpha decay, although is actually having the kinetic energy, but mass number and the proton number or the atomic number is a little bit larger. So that's why it is not so much penetrating. Uh, and there's another reason, like when actually alpha particle travel, the helium nucleus, which is actually an ionized nucleus after the alpha decay, would capture the electron or the electron from the air before traveling for very far. However, it is damaging as well because the alpha particle can knock atomic off the molecule, and obviously, if it is, let's say, like bombarded on the skin, or if it is actually touched on the skin, it's human skin, so it will knock off some of the molecules off, and definitely it will be a little bit irritating. uh, Alpha decay is most common in the element with atomic number greater than 83, obviously greater than the iron. Now we have got the beta negative decay. When a radioactive nucleus undergo a beta negative decay, the atomic number increase by 1 through the addition of one proton. At the same time, one neutron is lost, so the mass of the daughter isotope is same as the parent isotopes. Beta negative decay is more penetrating than the alpha decay because of the particle is so small. Beta electron can penetrate to about 1 inch of the flesh or the skin before they are brought to a halt because the electrostatic forces. In beta negative decay, or it is most common when with the high neutron and proton ratio. So let me tell you like what is actually why we have got the increase in a proton and decrease in a neutron. So when we have got the high neutron and proton ratio, so the neutron itself would emit an electron, as actually we have discussed in a previous lecture as well. By emitting an electron, it will become positive and become a proton. So an element, by emitting an electron from its nucleus, would convert into proton. When neutron is converted to proton, the atomic number is actually increased by 1 as the addition of proton, while the number of neutron and proton, as the number of neutron and proton are same, so the atomic mass would remain constant. So for example, the carbon 14 or carbon 6, atomic number 6, would convert to nitrogen 7, atomic number 7. So the carbon atomic number would be increased by 1, while the atomic mass would be same by emitting an electron. So this is the common example of beta negative decay. So that's what actually I've already explained, that the neutron will be emitting its electron by converting itself into a proton, and obviously the increase in a proton would be actually uh, transmutate into the element with a high atomic number, while the atomic mass would remain constant. Um, Now let's say like in a beta negative decay, as it was in an alpha particle, we said like the when there is actually energy release in a form of kinetic energy. So the most kinetic energy in alpha decay was taken by the helium particle, while in beta negative decay, as we can see over here, that the most kinetic energy should be taken by the electron, which is emitted from the nucleus. But experiments show that it turned out that the third particle, um, or in other words, would actually say like that the experiments sometimes show that some of the energy was missing, that the total energy taken by the electron was not the total energy, but some of the energy was missing. It turned out that the third particle was being released during the beta decay, and it was called as neutrino, named by the Fermi and proposed by Pauli. The neutrino is given a symbol of mu, and antineutrino is given a symbol of mu bar. The neutrino has the following property: where the particle which actually release during a beta decay, it has got zero electrical charges with no electrical charges. The mass much smaller than the electron, but definitely not zero. It has got weak interaction with the matter, so that's why it was difficult to detect, and only recently it was detected. So the beta in a beta negative decay, an electron and antineutrino is emitted. So the total equation or the balance equation energy wise would be the when the carbon is converted to nitrogen by addition of proton or conversion of neutron into proton by releasing an electron, and what we call it as an antineutrino. Now, on this the same concept would be actually for the beta positive decay. Beta decay occur when the nucleus emit an electron or positron, positive electron, and a type of neutrino in a process that changes a proton to a neutron or the neutron into a proton. So nucleus may capture an orbiting electron, converting a proton into a neutron, and that's what we call it as electron capture as well. The, the positron is formed when the proton break into neutron with a mass and no change, the mass having no change, and positron with a mass no mass on the positive charge. In other words, what I'll say like the positron like is formed by breaking a proton into a neutron with a mass and no charge, and a positron with no mass but a positive charge. So positron emission is most common in a higher element with which we have got a low neutron but a higher proton ratio. So proton is converted to a neutron by capturing electron. So in this way, what we call it as a when a parent nucleus is converted to a daughter nucleus, in which the proton is converted to a neutron. So that means like the number of proton would decrease, so atomic number would be decreases, while the addition of atomic addition of a neutron, but the difference of the rejection of a proton, the total neutron and proton will be the same. Uh, and by emitting a positive electron, what we call it as a positron, and the neutrino. So nitrogen would convert into carbon by releasing a positron and a neutrino particle. Now going forward to another type of a decay, we call it as a gamma decay. So as we have studied like both of the alpha decay and the beta decay, they are both result in element transmutation. That mean like the element is transformed from one element to another element. There is actually a radioactive decay which does not result in element transmutation, and that decay is called as the gamma decay. The energy of the excited nucleus may be emitted as a gamma rays or in a gamma decay, or used to eject the orbiting electron by interaction with the excited nucleus, and that is called as the internal conversion. So what normally would happen, like when we have got a decay process, whether it's an alpha decay process or a beta decay process. So normally or occasionally it will be result in change of element from one isotope to another isotope. Now, in many cases, the nucleus that undergoes a radio decay process is left in an excited state. The nucleus can then undergo a second type of a decay in which actually there is no change in a nucleus, but there is actually release of a high energy photon. These high energy photon are called as gamma radiation. It is actually a radiation in which it is the in other words, it is kind of a radiation in which we call it as a de-excitation process, and that is what is actually uh, high energy photons or high energy relative to energy of the visible light are actually emitted in a gamma radiation. Gamma decay can result from a collision with one another particle, but it is more common to see that gamma decay results after alpha decay or a beta decay. So let's say, for example, when we have got a parent nuclei converted into a daughter nuclei, and we have got the same element, but that same element is actually in an excited state, and then by release, when it is actually going towards the stabilization, it is actually releasing its gamma radiation. For example, boron is converted to carbon in a boron is converted to a carbon in a beta negative decay by releasing an electron and antineutrino. Now, this carbon, which is actually formed by beta decay, is still in an excited state. It still has got energy in it. So, this energy is released in a form of gamma radiation or gamma decay, and to become the carbon become more stable. Now, uh, note that again, gamma decay does not result in any change in our atomic number or atomic mass. Gamma radiation is the most penetrating at all. It has got the high energy photon with it, and it can cause severe damage. And that's what we call it, like in a nuclear fission or a nuclear bomb. If I say like the most damaging thing occur when we have got the second kind of a decay in a nuclear process, and that second decay is actually a high energy photon in which actually the human skin, or if I would say like in any other thing, it get excited or get ionizing, it can damage anything which actually come into its way. um, Electron capture, we have already said a little bit about the electron capture. When a nucleus of excited nucleus, when capture an orbiting electron from outside, uh, uh, then that would mean like the neutron would be converted to a proton by, and then when it is converted to a proton, sorry, the proton. When capture an electron, it will be converted to a neutron. So that means like atomic mass would be uh, same, while the atomic number would be decreased by one. This is called as the electron capture. There are other kind of decay process as well. Some of decay are like some of decay are spontaneous fission, and many other decay in and many decay process actually you can find it in a fission process as well. Now there is another important aspect of nuclear radioactivity, and that is what we call it as a half-life. Um, the half-life of the radioisotope is the time it would take for half of the atom in a pure sample of the isotope to decay into another element. So if you have got, let's say, for example, 1 kg of a substance, and it is decayed into another substance by any mean, like alpha decay or beta decay, but when actually it converted from 1 kg to a, let's say, 0.5 kg, so that's what we call it as a half-life of that element, and when we got it. So it's a measure of the stability of an isotope. The shorter the half-life is, the less stable is the element. So that means, like, when the radioisotope is converted from one form to another form, so if it has got a shorter life, so it is actually less stable. And it has got, if it has had got a longer life, so that means like that element is much more stable. So for formula for the half-life is over here, that so y is equal to y naught c raised to power t by t. Y is the final amount of the substance. Y naught is the initial amount of the substance. C is the constant of proportionality. In this case, we are trying to find out the half-life. T is the time, and T is the time cycle or the half-life of the substance. To be mentioned over here, like the decay of an element is said to be spontaneous, as one can only determine the probability of the decay, not predict when an individual element would decay. Let's say, take an example of the Stonehenge. The Stonehenge, if I would just say, like, if you have seen a Windows XP wallpaper, that scenery, that the stone which is actually there is actually called as the Stonehenge site. It's like the Stonehenge is an ancient megalithic site in southern England. Some believe like it was designed to make astronomical observation, but archaeologists cannot agree on the reason that Stonehenge was constructed. So the charcoal sample that was taken from the series of the hole on Stonehenge, they have taken, and it's like they have about like 0.63 pound of carbon 14 in 1 pound sample. So estimate the age of charcoal pit at Stonehenge, assuming that the half-life of the carbon is 14, is 5,730 years. So we have got the final amount, which is actually 0.63. We have got the initial amount, that is 1 pound. Let's say, like, over here, we have got the we want to find out the half-life, the constant of proportionality is the half. We need to find out the time of the Stonehenge where when it was built up, and we know the half-life of the carbon, which is 5730 years. So taking them over here, you can find out like the time, as the other unit was in year somewhere. Yes, so we can say like the time over here is like the Stonehenge is around 3820 some around years old. Now in this example, like the previous example, Stonehenge, if I would say, like, it's been used in the carbon dating, what we call it, phenomena, or the method we call it as carbon dating, in which, like, many ancient artifacts, or many ancient things, ancient things are actually carbon dated to check like when it was actually dead, or how old is this substance or a material, something. um, but the radioactivity or radioactive elements are much more common in used in uh, the process, or what we call it as a nuclear medicine, and in nuclear medicine we call it as a chemotherapy. If you can, if you have heard that name. So in chemotherapy, we have got much more radioactive medicine, which is taken by the patient, and that is actually designed, or these elements, sorry, these medicine are actually formed because, or another way, like these medicine are taken to target different tumors or different things, to kill it, or to make it possible to cure that organ. So let's take an example. Like, for example, I would how long it would take for 256,000 gram of thorium 234 to decay to 100 grams. The half-life of thorium is 230, half-life of thorium 234 is 25 days. So taking the same thing, I would say like y is equal to y naught and so on and so forth. So it will take 8 half-life of 25 days. So that means like the to decay from this much 2,500 256,000 gram of thorium to 1,000 gram, it will take only 200 days. So obviously, the patient does not take this much of thorium off. If I'm saying like the thorium might not be actually taken as a nuclear medicine, but yes, this amount of thorium is actually decayed into 100 grams on 100 sorry 1,000 gram in only 200 days. Um, we have already discussed about the radioactivity, but there are so much severe effect um, of the biological effect of the radiation. Yes, we will discuss the advantage of the radioactivity as well, but we have got biological effect. I would just say like if it is like not damaging reproductive damage to non-reproductive cells, we call it as somatic, and if it is actually damaging to reproductive cells, we call it as genetic. So there are is actually much more. If I would say like if a ray ionizing ray break down into molecule into living cell causing radiation that would burn or fatally injure the cell, damaging the growth of the cell. But in a, if I would say like another nuclear thing, if it is a cancer patient, so it will actually lead to damage can lead to a growth of cancer cell, and even like in other nuclear radiation, the cancer cell are actually bombarded with the nuclear radiation to kill it. While that's what actually we can call it in a nuclear the good effect of a nuclear. But if it is, let's say, for example, if we have got the ionizing radiation, and it is and human is exposed to that ionizing radiation. So if it is exposed for seconds, actually, so it will damage the DNA strand. It will break the DNA strand. It will have the oxidation damages. Oxidation damages mean like the skin will get dry, the lips and every the eyeball would get dry. So that means like it will be having an oxidizing oxidative damages as well. Now, if it is like say if a human is exposed to a minute actually, so there will be a gene expression change. There will be protein modifications. If you have seen a chemotherapy patient, so their nails are actually damaged. Their hair are damaged because they have been exposed to ionizing radiation, and that is for a longer time. So that's why they have got some protein modification. Now, if it is, let's say, the radiation is for hours, so it will cause the cell death. It will have the genomic instability. Then we can have the acute syndrome. We have got the organ failure. We have got the cancer, birth defect, gene pool defect. You might not have like come to, or you might have come to the news, different news, like USA. They have used the depleted uranium in Iraq. They have used depleted uranium bombs in Afghanistan, northern Afghanistan. So if you have seen much patient coming to Pakistan from the Afghanistan, they have got these birth defect, they have got cancer, they have got gene pool. It is because of the radiation effect that was used, or the bomb that was used by the American in their war on these two countries. So they have got in these countries we have got much more severe acute syndromes. We have got some organ failures over here. So this is actually a negative effects of the radiation, I've said. But yes, as we have a little bit discussed as well, there are some positive aspect of radiation or radioactivity, and one of them is actually the treating the cancer patient, nuclear medicine. And yes, and there is another positive about that is actually nuclear agriculture. So you might have heard just recent news like the cotton crops of Pakistan that is increased by the copper yield, the cotton yield is increased by 35% because of this nuclear agriculture. So that's a positive side of the nuclear radiation or nuclear uh, phenomena is. But there is actually like a much more severe damaging causes as well, and that is because if it is used uh, in some kind of a bomb that's been used by United States mostly on other countries. Um, I would understand like this is not the total lecture which actually I've delivered to you people. I would suggest like if you can just search about different aspects of this radioactivity, half-life as well, nuclear medicine as well, nuclear agriculture as well. So that would be much beneficial to you. Thank you very much. If you have got any question, you can actually post in a Google Classroom. Thank you.